All right, so we've done direct proof. We've done contrapositive proof, which is basically rewrite it and then do direct proof. But there is another proof technique that is a different approach that's super, super useful. And this is called proof by contradiction. So mathematicians are lazy and we like to have notation. So we get tired of writing the word contradiction. So the thing I use that I was taught is like a lightning bolt striking ground, okay? So I'll put that quite frequently. That means, oh, we've reached a contradiction. Some people will put arrows, butting heads. I've seen before an equal sign kind of X'd out, okay? All these different symbols meaning this is impossible. It's a contradiction, okay? So here's the idea. We are normally trying to prove a statement like P implies Q, right? Think your truth tables. What's the one situation where P implies Q came out false? Yeah, is only false if P is true and Q is false. Okay, so proof by contradiction says, I'm going to consider that case and show that it's impossible. So want to show this situation is impossible. So you'll see, yeah. Yep. Okay. Another way to view this, if you look at truth tables, P implies Q is the same as not P or Q. Some of you got confused with this on the homework where you had to negate conditionals. You were having a hard time negating conditionals. But P implies Q is logically equivalent to not P or Q. They have the exact same truth tables. So what do I get if I negate that? P and not Q. So this is another way to describe proof by contradiction. I'm going to assume P and not Q and show that actually can never happen. If P and not Q is impossible, then its negation, the original, is true. It always happens. Okay. So what do I mean by impossible? This is what makes proofs by contradiction a little less obvious than other ones. Impossible really means you come to some fact that can't be true. Like we're going to have one or multiple ones, I think, where we show 1/2 is an integer. You go, 1/2's not an integer. Apparently none of this was true. Okay. We'll get, in this first example, we'll get a fraction that can never be put in reduced form. Okay. Well, every fraction has a reduced form. Every rational number has a reduced form. Okay, so that's impossible. So apparently none of this was true. Okay, so that's how proof by contradiction works. Some people love it and it's their favorite proof technique and they want to use it on everything. Some people hate it and want to avoid it at all costs. Okay, it just depends on, I don't know, the way your brain works. So, all right, so let's see an example of what the heck I'm talking about. So this one, I'm not going to do the scratch work for. We're just going to write out our proof. Oops. Okay, so I want to assume the opposite of the statement. The statement is that square root of 2 is irrational. So what's the opposite? It is rational. So we will assume for contradiction square root of 2 is rational, is an element of the rationals. Okay. All right. Well, What does it mean to be a rational number? Yeah, to be a rational number. So this means square root of 2 equals a over b for a and b elements of integers, b not 0. Now, there's another thing we can add. We haven't added this to rationals before, but this can be in reduced form, right? So we'll say, so a and b are integers, b is not 0, and a and b have no common factors. All right. Okay, let me, there you go. All right, so they have no common factors. Well, now we just do some algebra. So take a look at that equation. Square root of 2 equals b times a. So let's multiply both sides by b. So then square root of 2b equals a, which gives us, let's square both sides. What do I get? I get 2b squared equals a squared. All right. What does that mean about a squared? What type of integer is it? It's even, right? It's 2 times something. 2 times an integer is even. So a squared is even. Okay. But what's that mean about a? If a squared is even, what's that mean about a? Well, so is a even or odd? Has to be even, because what have we proven? We showed if a is odd, a squared would be odd. So the contrapositive would be a squared even implies a even. Okay. But this can only be true if a is even. So now we're going to do what you were saying of what does even mean. This can only be true if a is even. So there exists k in the integers with a equal to 2k. Well, let's put that into our equation. So now our equation becomes 2b squared equals 4k squared. All right. Well, I can simplify that. Divide both sides by 2, right? We can write that. Divide both sides by 2 to obtain so divide both sides by 2 to obtain, and what will we get? B squared equals 2k squared. But wait, what does that mean about b? B is even, because b squared is even, therefore b is even. So, so similarly, or similar to above, however you want to phrase it. B is even. But why can't B be even? Yeah, that fraction was supposed to be in reduced form. It was supposed to not have common factors. I just found a common factor. That's the contradiction. And it doesn't matter. You could say, well, maybe you messed up. So divide them both by 2. Now you've got reduced form. I could do this exact same process again. Say, nope, they're both still even. Okay, and you say, well, divide out that 2. Be like, nope, they're both still even, right? This will always happen. No matter what A and B you start with, you'll always get them both even. So that's our contradiction. So here we go. But A and B have no common factors. Here's where I put my lightning bolt, okay? And that's signaling that that's my contradiction. I've reached my contradiction, okay? That's the impossible thing. How can they both be even and have no common factors? Okay, all right. So what was the assumption I made to start with and followed all this logic that ended up being impossible? Yeah, that square root of 2 was rational. So apparently it can't be, because if it was, math would fall apart as we know it. So it can't be, okay? So square root of 2 is not an element of the rationals. That's how a proof by contradiction works. This is the classic proof by contradiction, by the way. There's one more classic one. We'll see if we get to it today. But would this same argument work for something like square root of 3? Yeah, so you'd have to do a little more work, but the same idea would end up working. But when I get to this here, I'd have 3b squared equals a squared. I would have to justify that a has a factor of 3 in it, and we haven't done that work. But if you could justify a is a multiple of 3, and then and then get b a multiple of 3, the same logic would work. Okay. We just haven't justified that much yet. Whoa. There you go. Okay. So let's look at another one. All right. So here we go. This equation has no integral solutions. That integral, that means integer. So it has no solutions that are integers. No integers, x and y, can make that equation true. Any thoughts of what might go wrong? So this is how proof by contradiction works. What would go wrong if x and y were integers? Why wouldn't it equal 5? Why couldn't it? I'd have an even plus an even equal to an odd. That's not possible. So there's our proof by contradiction. Okay, so here you go. So proof. Suppose for contradiction, there exist x and y in the integers such that um, 2x plus 2y equals 5. All right. So there are 2 ways to do this contradiction. The one we said of even plus even can't be odd. The other way would be to divide both sides by 2. We would have integer plus integer equals 5 halves. But an integer plus an integer is an integer and can't equal 5 halves. So let's do the even way, but you could have gone about it the other way. Note that two x and 2y are even. Are even Therefore, their sum is even. And that is something we've shown in class, right? We showed if you add two things that are opposite parity, it comes, or same parity, they come out even. So we've shown even plus even is even. Okay. But 5 is not even. So that's our contradiction. So I put my little arrow. Lightning striking. Thus, no integers x and y have 2x plus 2y equal 5. And again, if you wanted the alternate, so I'm not going to write it out, but would be divide both sides by 2 and you get x plus y equals 5 halves. And this side's an integer and this side's not an integer, so that is a contradiction. Okay, that'd be another way to get the contradiction. Any questions on that? All right. Let's do the next one. No integer is both even and odd. This is an example of one that you read and go, duh, right? Okay, but we can't actually prove it with contradiction. So what are we going to assume for contradiction? Yeah, that there's some integer that is both at the same time, right? That is both even and odd. What happens? So assume there exists, I'm going to call it A in the integers. It is both even and odd. Well, what's it mean to be even? So then there exists a k in the integers with a equal to k. And what's it mean to be odd? There exists an L, right, in the integers with a equal to k plus 1. Or 2L plus 1. Oops. Shame on me. Okay. What do you think? What can I do now? Set them equal. If they both equal A, they have to equal each other, right? So, but this means two k equals 2L plus 1. So I'm going to do a little bit of algebra in my head. I get k minus L equals 1/2. Everybody agree with that? The algebra comes out k minus L equals 1/2. Why is that a problem? K minus L is an integer. 1/2 is not an integer. So since k minus L is an integer, we have 1/2, an element of the integers. That's definitely a contradiction. That is not possible. Okay. And our initial assumption was that A was both even and odd. Ergo, A cannot be both even and odd. Now, technically, we didn't show that every integer qualifies as either even or odd. We technically have just assumed that, right? We never showed that there weren't any integers out there that are neither. That requires the division algorithm to do. I don't think we'll do that, but it's not too bad. But so you can assume, and we have been assuming, if it's an integer, it's either even or odd. And now we know for sure, even though we've been assuming it, it can't be both. Okay. All right. Any questions on that one? Yeah. I can't hear you. Ergo, that just means so, therefore, hence, since. Yeah, I just get tired of writing so, then. Yeah. Yep. All right. Yeah, feel free to use ergo and impress or throw off your other professors. I don't know. Okay. All right, so this is probably a good stopping point for this first bit of contradiction. Let me give you a little bit of language though. So on the next page, you'll notice I have something called a lemma. Typically we call something a lemma if we are going to use it for the next thing we prove. Okay, that way I can just reference it in the middle and say, and by the lemma, blah, 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 happens. Okay, so we're going to need this lemma, this fact, in order to prove there are infinitely many prime numbers. And that's where we'll start on Thursday. Okay, so